Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online course on techniques of materials characterization. We are still continuing with module 9 and we are discussing now X-ray diffraction, and until up to now we have discussed about the history of X-ray diffraction, not only diffraction, the history of X-ray, then how X-ray diffraction came in by the Braggs, and then we discussed about X-ray source signal, how the X-ray is generated. We discussed about continuous spectrum, we discussed about characteristic spectrum, and in the last class we just begin with X-ray absorption, and that we will be continuing now. We are like in this lecture 5, and today we are going to cover this few issues: X-ray absorption, mass absorption coefficient, absorption age, and OJ effect. OJ effect, already we have discussed about OJ effect during our lectures on SEM, but again we will be discussing a little bit about OJ effect in terms of X-ray signals. So, this we discussed in the last class. X-ray absorption, we said that X-rays encounter any form of matter, some part of that X-ray will be absorbed by the matter or absorbed by the material, and some part goes out, and that is the basis of this radiographs, where your flesh is transparent, virtually transparent to X-ray signal. That means they are not absorbing X-ray, whereas the bone part, which is more dense part, they will absorb X-ray. Most part of X-ray will be absorbed, and that is why on the back side in the photographic film you will be getting an contrast accordingly. So, wherever the X-ray is fully transmitting, not absorbed at all, those areas will be appearing in brighter contrast, and areas where the X-ray is absorbed, obviously on the other side the intensity of the X-ray will go down and you will be getting a darker contrast. So, that is the basis of radiography, and today we will be discussing from there something else called mass absorption coefficient, and before that we will discuss about linear absorption coefficient. So, this decrease, if we now think about any material of a finite thickness, and this is the X-ray source, and this from this side, this is the intensity of the X-ray that is hitting this material, and on the other side if we measure the X-ray intensity, then what we will be seeing is that the decrease in the intensity of the X-ray beam as it passes through this material, this is proportional to the distance it travels. So, this is by simple experiment you can find it out that this is what is happens. So, X-ray, the amount of decrease in the intensity of the X-ray between the incident X-ray and the transmitted X-ray, the amount of the intensity that is decreased, or rather the amount of X-ray intensity that is absorbed by this material. So, this fractional decrease is basically proportional to the distance, or rather to the thickness of this material. So, if we write this down, we will be able to write this kind of a relationship, that is minus di by I. So, di is basically the decrease in intensity divided by the original intensity. This is proportional to the distance that it travels, and the proportionality constant for this relationship mu, that is called the linear absorption coefficient. Okay. And this linear absorption coefficient, as we will be discussing more, this depends on the material constant. So, that means this depends on the kind of material, the elements that forms this, and so on, the atomic number of those elements and so on. So, basically it depends on what kind of a material it is, the density of the material. So, how dense this material, whether this material is only composed of same kind of material, or there is another phase is present, and so on and so forth. So, density of material, basically how many atoms are there in the path of the X-ray, that is it. And the wavelength of the X-ray. So, wavelength of the X-ray means the energy of the X-ray. So, if the energy, if it is a very high energy X-ray, then obviously that will not be absorbed that much, it will be penetrating, mostly penetrating. So, the energy of the X-ray will also be important. So, these three things we will be discussing, and it will make more sense when we discuss about something called absorption age and so on, and then we will realize what is the effect of atomic number, what is the effect of density or energy, X-ray energy, whatever. But to understand this linear absorption coefficient, sometimes it is also called linear attenuation coefficient. So, we imagine that there is something like 100 number of X-ray photons which are coming from this side, which is an incident X-ray photon, that is 100 number, and out of that 10 number of photons are getting absorbed by this material which is around 1 centimeter thick, and this side we are getting around 90 atoms. Okay. So, that means this dI, that is I naught minus Ix basically. So, this dI of course is 10, I, the incident X-ray intensity is 100 here, and dx, the thickness is 1 centimeter. So, this one finally makes mu, that linear absorption coefficient, becomes 0.1 per centimeter. Okay. So, that is the unit of mu is basically centimeter inverse. So, this linear absorption coefficient now can be expressed in terms of this distance, inverse distance, and it is coming out to be 0.1. If this is the relationship, 100 amount of X-ray photons are hitting this material and 10 of them getting absorbed, 90 of them getting transmitted. So, the linear absorption coefficient then over a distance of 1 centimeter, linear absorption coefficient is 0.1, clear, fine. So, if we integrate this equation, then what we will get is Ix, of course, Ix is the transmitted intensity in this side, equals to I naught, that is the initial intensity or incident intensity here, X-ray intensity, and Ix equals I naught into e raised to the power minus mu x, x is the distance it travels, total distance it travels, mu is the linear absorption coefficient. Okay, fine. As we said, the linear absorption coefficient of course depends on the density of the material. So, how dense the material, what is the density, the single phase material, multi-phase material, what is the density of the material. So, if we introduce the density here in this equation, what we see is Ix equals I naught into e raised to the power mu by rho into rho x. So, this is also another constant, mu by rho. Mu is a constant for any material as we just now discussed, and rho is another constant for that particular material and particular condition. So, this quantity mu by rho is called the mass absorption coefficient. Basically, mass absorption coefficient coming out of the linear absorption coefficient, just we are introducing, we are normalizing this with respect to the density of material. The linear absorption coefficient normalized with respect to the density of the material, that is what is giving the mass absorption coefficient, fine. And this mass absorption coefficient again is a constant for any material. More importantly, it is independent of the physical state of the material, whether the material exists liquid, solid, gas, whatever, it is independent of that, and what we will be discussing, it is independent of its state, whether it is existing in a composite form, mechanical mixing and so on. But if you, even if you take this, for example, let us say we take nitrogen, now we know that nitrogen is basically a gas, but if you sufficiently cool it down, if you press it and sufficiently, if you are able to cool it down all the way to minus 77 K, you can make it a liquid. Point is, the liquid nitrogen and the gaseous nitrogen, both of them will have the same mass absorption coefficient, that will not change. Even better, if you take an example of say water, whether it exists as a water vapor, whether it exists as a water as a liquid or as ice in solid, the mass absorption coefficient is not going to change. Okay? Whatever be the linear absorption coefficient divided by the density of the particular state, that will remain constant, that value will be constant. So, that means we will come to that. That means if the density changes, linear absorption coefficient will change accordingly, and together it will make this mu by rho constant irrespective of the physical state. We know the density changes, right? When between the water as a liquid and water as a solid, ice, there is a change in density. Ice is much more lighter than water, and that is why it floats over the water. So, that we all know. So, this density changes, accordingly the mass linear absorption coefficient changes, and that makes the mass absorption coefficient constant. So, this is the importance of mass absorption coefficient. That is why we are sort of normalizing this on top of the linear absorption coefficient. Linear absorption coefficient changes with the physical state, but when we normalize with respect to the density, what we will see that mass absorption coefficient does not depend on the physical state. That's the point. Okay. So, now the linear absorption coefficient, of course, as we understand, this is proportional to the density rho, okay, and from there we are getting this relationship, and this quantity is of course called the mass absorption coefficient, just now we discussed, which is independent of its physical state, okay. So, now if we see this example, one more example, we are considering this two materials, same materials, blocks, and we are seeing that when the 100% out of the incident X-ray, 90% is getting transmitted for both of them, 10% is getting absorbed, and their thickness or the distance that X-ray beam travels, that also is different, but their mass absorption coefficient is different because the density. So, linear absorption coefficient, if I take linear absorption coefficient, only depends on the distance it travels and the amount of the absorption. Amount of absorption, just like what we discussed, amount of absorption here is it's 10%. The thickness, if we take the thickness is 1 centimeter, linear absorption coefficient is 0.1 centimeter. If we take the thickness of this material is slightly longer, linear absorption coefficient will also change accordingly. What will remain constant is basically mass absorption coefficient, because the density of the material is changing between these two, okay, and the density change in density. So, the density of this block and the density of this block will change accordingly, the volume will change and the density will change, and we will be getting the same mass absorption coefficient for both of them, right. So, that is the point, or that is the importance of considering mass absorption coefficient instead of linear absorption coefficient. Okay. Now, mass absorption coefficient, another important point is mass absorption coefficient of a composite material, of a material, multi-phase material or a composite material containing more than one element. So, whether the substance is a mechanical mixture, that means you have two liquids mixing, maybe you can, the best example you can take a solution where two, let us say water and oil solution which is not going to mix, or a water and alcohol solution which is a miscible liquids, or two miscible liquids forming a solution. You have a mechanical mixture, let us say you have an alloy of any sort, any iron based alloy, ferrous alloy or so, or you have a chemical compound, you take any of these polymers, you take water for example, whatever, and whether that composite or mechanical mixing or mixture or solution or alloy, whatever state it exists, solid, liquid, gas, whatever state it exists, the mass absorption coefficient is the weighted average of mass absorption coefficients of its constituent elements. So, if you consider for example, W1 and W2 are the weight fractions of two elements. So, your composite, let us say your mixture or your solution, water and alcohol solution, it is composed of say two or for even better, if you take something like an alloy of two different elements. So, that two elements, let us say you consider a titanium aluminide, which is titanium and aluminum. So, and the weight fraction of these two, titanium and aluminum, is W1 and W2. The mass absorption coefficient of these two is mu by rho 1 and mu by rho 2. Then the mass absorption coefficient of the entire composite substance, entire intermetallics, will be just a simple weighted average W1 into mu by rho 1 and W2 into mu by rho 2. That will give you the mass absorption coefficient of this composite material. So, simply this is how you can derive the mass absorption coefficient of any material just from its constituent element. Does not matter which state they are, does not matter how they are mixed, does not matter whether they are, it's like a physical mixture or a chemical mixture, nothing. It just depends on the chemical nature of those constituent elements and their weight fraction, that is it. So, that means the mass absorption coefficient is a very, very general concept and very, very generalized property for any material in terms of absorption, X-ray absorption. Okay. Now, Let us then see another concept, that is called absorption age. What happens in the X-ray absorption? What is the basis of X-ray absorption? What happens there? What causes absorption, and so on, and how we can use it for working with X-ray or using the X-ray source for characterization. Okay. So, the way in which the mass absorption coefficient mu by rho varies with wavelength of the X-ray. Wavelength, remember, wavelength and energy of the X-ray is two interchangeably. We will be using, these are two interchangeable quantities. So, if something is having a lower X-ray, is having a lower wavelength, means the energy of the X-ray is correspondingly higher. That is it. So, if we see this, that mass absorption, variation of mass absorption coefficient with respect to the energy of the X-ray, fine. So, what we can see, and this is shown for a nickel specimen, nickel absorber, nickel specimen, but it is very typical, and this same thing happens for most of the other elements, like if they are most of the metals, most of the transitional metals, this is the kind of graph you will be seeing for mass absorption coefficient versus the lambda. And this is how, again, the energy per X-ray quantum versus the lambda, this is the relationship, and you can see that when the wavelength is smaller, for shorter wavelength, lower wavelength, the energy of the X-ray beam is correspondingly very high. Okay. So, in this one, the curve shows two distinctly different branches, one is in this side, one is in that side, and this is separated, this side of the curve or this side of the branch is separated from this side of the branch by a sharp discontinuity. Very sharp discontinuity means this branch, there is a huge jump in the mass absorption coefficient over a very small wavelength range, and it increases by many fold. Okay. So, this increase here within a very short wavelength, this increase in the mass absorption coefficient is called the absorption age. So, this is happening for K absorption. K absorption age, we will come to know what is K absorption age, but this is something happening over a wavelength which is basically belongs to K characteristic radiation or K fluorescent radiation, that is why it is called K absorption age. But basically this jump or this sharp discontinuity is called the absorption age. Okay. Now, if we consider this two, other than this absorption age, if we consider these two branches, both of these branches, the mass absorption coefficient varies with wavelength following this relationship, mu by rho equals K lambda q ZQ. So, ZQ is basically the element, it also depends on what type of element it is, the mass absorption. The absolute shape of this one or the extent of variation depends on different material, but basically the shape of this is pretty much the same. The absorption age, the having an absorption age at what wavelength and all that, everything depends on the nature of the material, the atomic number of the material, but this basic shape, two branches separated by a discontinuity, that remains the same for almost all the materials. Okay. So, if we now see it more, one thing we can quickly realize that the mass absorption coefficient strongly varies with wavelength. Okay. And for shorter wavelength, if we come to here, the shorter wavelength, the mass absorption coefficient is much higher than the longer wavelengths, right. So, correspondingly, if we first thing we understand, if we just even do not consider this absorption age, but simply because of that absorption age, the presence of absorption age, shorter wavelength mass absorption coefficient of shorter wavelength X-rays are much higher than longer wavelength X-rays. That means X-rays which are much more energetic or high energy X-rays are more, can be absorbed more, and less amount will be transmitted or penetrated through anything. So, we can use this information to identify or to differentiate between the short wavelength or soft X-rays versus the hard X-rays, as we were discussing in the previously when we were discussing X-ray as a electromagnetic radiation. We have said that some X-rays, some wavelength of X-rays are used for medical purpose, and that is called the soft wavelength X-rays, and some of them are used for characterization, this X-ray diffraction or XPS or X-ray microcity, all of this, that is basically the hard X-ray, that wavelength of that X-ray is basically the hard wavelength. The reason for this is softer means when the wavelength of the X-ray is much smaller, then that wavelength that is less absorbing or that is more absorbing compared to the hard X-rays, right. So, this is less, this shorter wavelength X-rays are having higher energy and they can be, their mass absorption coefficient are much higher. So, they can be absorbed more and they can produce this kind of contrast or radiographic images, whereas the hard X-rays are more or less the wavelength is higher, the energy is correspondingly lower, and those hard X-rays are basically favorable or they are having less of a absorption, which is better for any kind of characterization like X-ray diffraction. You do not want the X-ray signal to be absorbed more by the material itself. It should just do the diffraction. It should not absorb. It should not. It should allow the diffraction or scattering rather than absorbing that X-ray. So, that is possible if you use an hard X-ray where the mass absorption coefficient is pretty much lesser. Okay. So, this is the difference between hard X-ray and soft X-ray in terms of the absorption of this X-ray signal. Okay. Now, how do this absorption happens? That is the question. So, matter absorbs X-rays by basically two distinct ways. One of them is scattering, typical X-ray scattering. Another one is called true absorption, and these two processes together make or together contribute to the total X-ray absorption. So, between an incident X-ray and the transmitted X-ray, whatever the X-ray intensity is lost in the material itself, that is contributed by both X-ray scattering and something called true absorption. So, scattering we have already discussed in terms of electron scattering. There we discussed different processes, elastic interaction, inelastic interaction and so on. Pretty much the same thing here. You have an incident X-ray electrons and then the X-ray electron either can just get deviated from its original path because of the Coulombic interaction, it gets deviated, or otherwise at special cases it is diffracted as well. So, whatever it is, whether it is a simple scattering or a diffuse scattering, that is what it is called, diffuse scattering, or it is a simple, or it is a diffraction or some other kind of inelastic interaction, whatever, that part of energy or that part of from the incident X-ray, that part of energy is lost. So, that is not getting transmitted in this side. So, we can imagine that this is the incident photon, this is called Compton scattering. We will come to this in the next module possibly. We will be discussing more about the Compton scattering, but basically this is the incident photon and some part of it is just getting lost as a scattered. So, if we collect the transmitted X-ray here, definitely this part, this much of X-ray intensity will not be present. So, scattering, unfortunately it does not contribute much for heavier elements. It is for a very light element, the scattering is responsible for the absorption, or it is having a significant contribution in the absorption, total absorption, for only for light elements. For heavier elements, scattering contributes to a very small amount in the total absorption. For those kind of material, for heavier elements, it is mostly something called true absorption. Okay. So, what causes the true absorption? True absorption is mostly happening by electronic transitions within the atom. So, this is basically an X-ray, true absorption depends on the X-ray material interaction. So, we have already seen electron material interaction, and there we have seen various different processes, inelastic interaction and there plasmon scattering, photon scattering, so on and so forth. And one particular process we have seen, that is electronic inertial excitation and secondary effects and so on. So, exactly the same thing can also happen when an X-ray photon encounters a material atom. Whatever the electron can do, the X-ray also can do, because both of them are electromagnetic radiation. There is no difference between as per their nature. Of course, electrons are charged particles, so there are some other things that happens with electrons, but forget about that. But basically, energetically, they are both electromagnetic radiation. Nature wise, they are both electromagnetic radiation, and they can pretty much do the same thing. Okay. So, just like an electron of sufficient energy can knock an K electron out of an atom, and that can cause an emission of K characteristic radiation as a secondary effect, the same thing can be done by an X-ray photon with a particular amount of energy, and if it contains certain amount of minimum amount of energy of Wk, which is basically the binding energy of the K electron, K shell electrons. In this process, Basically what happens is that the X-ray photon comes similar to the electrons, incident electron. Here it is an incident X-ray that comes, that knocks out a k electron from the k shell and creates an k shell vacancy, and in order to fulfill that, then we have an electronic transition from other cell, the electrons jumps back and it causes an characteristic radiation. So two things happens here, or two things are generated. One, an electron which is knocked out, that electron is called basically photoelectron, and a characteristic K radiation, K characteristic radiation, which is called fluorescent radiation. The difference is this K characteristic radiation, fluorescent radiation, is caused by an X-ray signal and not by an electron signal. So that is, or not by an electron. The source of signal here is the X-ray, not electron. That's the difference between a K characteristic radiation and the fluorescent radiation. Okay. Now this fluorescent radiation, it can go all direction, it can emit in all possible direction, but the wavelength of the K fluorescent radiation is exactly the same as the, or wavelength is same means energy also is same as the characteristic X-ray, K characteristic X-ray radiation, which is caused by the electrons when it encounters any metal target. When it generates, in the process of generation of characteristic X-ray, the electrons comes and hits the metal target, exactly the same process, but now we are, instead of electrons, we are considering the X-ray photons here. Okay. So basically this means an atom emits the same K radiation, and it's a X-ray radiation. It's a fluorescent radiation it's called, but it's basically an X-ray radiation only. So this X-ray radiation, an atom emits the same K radiation no matter how the K shell vacancy was originally created, whether it is created by the electrons or it is created by an X-ray quantity. It doesn't matter. All it matters is that this electronic transition should happen, because this electronic transition is what is causing. So this X-ray photon is interacting with the material and causing this photoelectron and K fluorescent radiation. Instead of that, if it is an incident electron, it will come, it will generate an electron, knock out an electron and generate a characteristic radiation. But this part is common, and the atom doesn't know whether it is hit by an electron or a X-ray. All it knows that this much of electronic transition should happen, and there should be an electron emits and K characteristic emission should happen. That's it. And this also, this process X-ray absorption phenomena, this also we can think it is an X-ray counterpart of photoelectric effect that happens in the ultraviolet region, where a photoelectron is emitted because of from the outer shell due to the action of an ultraviolet ray. Okay. So same thing happens here. Now the energy of this incoming X-ray, of course, just like characteristic radiation, there also we have seen that a critical excitation voltage is needed, and unless and until the electrons has a critical or accelerated through an critical excitation voltage, that will not be able to produce a characteristic radiation. Same thing happens here, that incoming X-ray also must exceed a certain, the energy of the incident X-ray photon must have a critical value, must exceed a critical value. Here is no acceleration is involved. It just the X-ray photon needs to contain that, needs to hit the metal or needs to hit the atom, material atom, with that amount of energy, incident X-ray itself. But the amount of energy, the value of that energy remains the same. So that is Wk. If we are considering K characteristic radiation or K fluorescent radiation, it is that same Wk amount of energy which we can equate it to h nu k, and in the process we can write hc by lambda k. Here lambda k is basically the frequency, mu k and lambda k are the frequency of and wavelength of K absorption age. Instead of calling it K characteristic radiation, now we are calling the Wk and lambda k. Wk remains the same. Wk is the same amount of energy, binding energy, that you need in order to generate the characteristic K radiation, or in order to cause this characteristic or this absorption age, to create that absorption age, whatever it is. But this lambda k now is the wavelength of K absorption age. Okay, fine. One thing we must understand is that instead of fluorescent radiation, we can also have an Auger effect. Just the same way we discussed this Auger effect in terms of the electrons, electronic transition, they are also the same way we can have an Auger effect, and we can generate an Auger electron instead of a fluorescent, X-ray characteristic fluorescent radiation. Instead of that, we can have a OJ electron generated here. It is a slightly different process altogether, because here what we can have is a K shell vacancy created by that incident X-ray photon, and then we can have an normal K radiation, emission of K characteristic radiation, or an OJ electron radiation. In OJ electron radiation, what happens is that the K shell vacancy is filled up from L shell, and already we understood, I discussed that L shell has various other sub shells or sub or orbitals. So, from any of those orbitals, let us say L2 orbital, we have this K shell vacancy is filled in from L2 level, and then the K radiation that emits, basically that K radiation, that is also an X-ray radiation, it ejects another electrons from L3 level, right. So, that electron, so instead of K fluorescent radiation coming out of the atom, that K fluorescent radiation causes, if it has sufficient energy, it can cause another electron to emit in the same process, photoelectron, another electron it can knock out, and that electron will be known as the OJ electron. So, OJ electrons, as that also we already discussed, that for lower light elements, instead of characteristic emission, it is mostly OJ electron emissions, and for mostly materials above 30, when the atomic number is above 31, it is mostly the characteristic radiation which is taking place. OJ electron emission is very less, whereas less than 31, mostly for very low light element, the characteristic emission is very low, and it is mostly the OJ electrons which emits. And the way we can differentiate between them is called the fluorescence yield and fluorescence yield. This also we discussed. Fluorescence yield depends is basically number of atoms that emit K radiation versus number of atoms with a K shell vacancy. For a very small light element, this is a very small value. The fluorescent yield is very small value, meaning that X-ray emission is very less, mostly it is OJ electron emission, whereas for heavier elements like copper, like moly, this is a very high value, fluorescent yield is very high. That means mostly the absorption happens by a characteristic K shell K radiation rather than OJ electrons, okay. And OJ electrons, already we have also discussed this, the OJ electrons are very good because the energy of the OJ electrons or the wavelength of the OJ electrons is also depends on the electronic transition. So, that generation of OJ electron again is related to electronic transition. So, they can be used for chemical analysis as well. Point is, OJ electrons gets very easily absorbed within the material. So, it is a very much a surface characterization process, and very within a depth of around 10 angstrom, from which this OJ electron, if the OJ electrons are coming from there, they can only escape the specimen surface and then can be detected. So, detection of OJ electrons is also a very big issue. Altogether, OJ electrons is a fantastic way of doing chemical analysis. Only thing, the detection and the instrumentation is a problem. So, we will stop here and we will continue with this absorption age or X-ray absorption in the next class.